Hello everybody. This is our video number 2, and hopefully I will have this posted for you sometime on Sunday, at the latest on Monday. So, like I told you, the first thing we will always do in any class, either on video or on in face-to-face, we'll go over the homework. So, let's go over the homework that was assigned, and your homework from class was on page 2. It started on page 20, I believe. At least I hope. Okay, what I've got here, and again, I hope I gave it to you correctly. Hopefully these were your homeworks. Page 23-6. And page 32, numbers 1, 6, 8, and 18. If somehow I did that incorrectly in class, I'm sorry. I'm not used to this no interaction thing with just the computer. But these are the problems I'm going to go over, and hopefully we'll answer any questions. Again, there's no interaction, unfortunately, but if you have questions, please feel free to call me or email me. So these are the ones I'm going to go over. Alrighty, on page 20. One second, I've lost my glasses. There we go. Alrighty. We talked about, in here we talked about points being collinear and betweenness, and we talked about things you can and you cannot assume. And on page number 20, number 3, they gave you that figure, and they asked in part A, name all the points that are collinear with E and F. With E and F, the points that are collinear with both E and F are E, F, B, and D. E, F, B, and D. Again, let me just draw a figure so you had E, F, B, D, C, and A. Now, if I didn't mention it, and I don't think I did, when you see this little box at the corner of an angle, what they're telling you is that angle is a right angle. So anytime you see a little box at the corner of an angle, that is the designation for a right angle. And I'm sorry if I forgot to mention that. I believe I did. Alrighty, and remember, those are called tick marks. Those are, it means that those two pieces, AB and CB, are equal in length, therefore they are congruent. They're marked the same. So again, part A, the points collinear with E and F, you can assume straightness. You can assume, therefore, that this is a straight line segment. Therefore, E, F, B, and D are collinear. It said, are G, E, and D? Are G, E, and D collinear? The answer is no. They do not lie on the same straight line or line segment. Are F and C collinear? All right, now think about this one for a second. Are F and C collinear? Well, there's no line segment drawn there, but does that necessarily mean they're not collinear? And the answer is they are collinear. Any 2 points can be connected, forming a line or line segment. So even though the line segment or the line is not drawn in there, you can say that F and C are collinear. As a matter of fact, you can pick any 2 points on this figure and say that they are collinear. Like I can say A and F are collinear. Even though they're not connected, it doesn't matter. It just means, would it be possible to draw a line or line segment that those 2 points lie on? And the answer is always yes. 2 points determine a line always. Which 2 segments do the tick marks indicate that are congruent? AB and CB, or AB and BC, however you want to name it. They have the same marks, they're congruent. Is angle A congruent to angle D? Is angle A congruent to angle D? From what I just told you a second ago, the little corner box at the corner means those are right angles, and right angles equal 90 degrees, and 2 angles that have the same measure are always congruent, therefore, and we proved that theorem the other day, your first theorem. All right angles are congruent, so angle A and angle D are congruent. Is angle F congruent to angle ABF? Is angle F, I've got these marked. This is E and this is F. Is angle F congruent to ABF? Are these 2 angles congruent? You cannot state. They're not marked congruent. They might look congruent, but you cannot say definitely that they are. So the answer is not necessarily, you don't know. Where do lines AC and FE intersect? Now remember, they said line FE. So that means if you go through F infinitely either direction, where do these 2 lines intersect? They intersect at point B. What is the intersection of line segment AG and line segment GF? Well, here's AG. It starts at A and goes to G and stops. Line segment GF goes from G to point F and stops. This line segment and this line segment only have 1 point in common, point G. G is the point of intersection of those 2 line segments. And again, that upside down U means intersection. Hope you remember this from algebra. If it were a U, that means union, all points, common to both. And that's what part H is. AG in union with GF. Line segment AG in union with GF. That means every point on this segment plus every point on that line segment gives you the whole segment from A to F. So the answer for G is line segment AF. For H, the answer I. B lies on a ray whose endpoint is E. B lies on a ray whose endpoint is E. Name this ray in all ways that you can. All right, so easy endpoint, and it goes through B. It has to go through B because I told you B was on the ray. So you're thinking about the ray from E through B infinitely. Therefore, you can call it ray EB or ray ED, nothing else. B lies on the ray, you can't use that as the endpoint. And then a ray has one and only one endpoint. In this case, they told you it was point E. So the only way you can name the ray that starts at E and goes through B is ray EB or ray ED. If you want to use 3 letters, EBD. They have to be in order that they show up. And the last one, J, name all the points between name all the points between F and D. Between F and D, all the points that are in between, there are only 2, E and B. No others lie on that straight line and are between these 2. E and B are the only 2. So that's number 3. Now, we talked about algebraic equations the other day. Here's your first one. In number 6, it said that this angle, they gave you angle A, B, C. They told you this is a right angle. Again, the box at the corner means it's a right angle. Angle ABD is a right, or ABC is a right angle, and they told you that the ratio of the measure of angle ABD and angle DBC is 3 to 2. The ratio of angle ABD and DBC is 3 to 2. Now, again, the drawing is only a visual aid. It doesn't have to be to scale. It doesn't. What's important is what they tell you about it. So the way I've got it drawn, they look like they might be equal. It looks like this might actually be smaller than that, but then they told you that this angle in ratio to that angle is 3 to 2, which means if I call this angle's measure 3x, that angle measure is 2x. 3x over 2x reduces to 3 over 2. And what do I know about the two angles when added together? The two angles when added together form a right angle, which is 90 degrees. So your equation is 3x plus 2x has to equal 90. So 5x is equal to 90. Divide by 5, and you get x is equal to, what, 18? And then they asked you, once you've got that, what, it said find the measure of angle ABD. Well, angle ABD is 3 times x, so 3 times x is 54 degrees. 3 times 18, 54 degrees. Making the other one 36, because 54 and this angle have to add up to 90, so the other angle will be 2 times 18, or 36. Hopefully everybody understands that one now. The last one, or next one on this page was 7. Explain how the sum of two acute angles could be. Okay, hopefully everybody's got this. Remember, we defined an acute angle as an angle greater than 0, less than 90. And they said, how could the sum of two acute angles be also acute? How could the sum of two acute angles be acute? Well, in order for them to be acute, that means when you add them together, they have to be less than 90. Greater than 0, less than 90. So in order to get two acute angles adding together, two angles added together and be acute, well, first of all, they would both have to be acute to start with, like 30 and 50. 30 is an acute angle, 50 is an acute angle, 30 plus 50 is 80, which is still less than 90, which means that they are added together and less than 90. So anytime you have two acute angles whose sum is less than 90, then then you have the sum being also an acute angle. Anytime you have two angles less than 45, they have to, when added together, be less than 90. But you can also get two acute angles that aren't both less than 45. In the example I first gave, 50 plus 30. 50 is bigger than 45, but it's acute. 30 is less than 45. 50 plus 30 is 80. The sum is less than 90, so it's acute. But you're guaranteed, if both angles are less than 45, then the sum will always be less than 90, so that's another way you can figure it out. So again, there's two ways. Start off with two angles less than 45, then the sum of the two has to be less than 90, which means that the sum is acute. Or one angle could be any acute angle, 60. The other angle has to be such, it has to be acute also, but so that when you add it to 60, your sum is less than 90, so it would have to be an angle less than 30. 29, 28, 26, 29.5, 60 plus any of those numbers less than 30 will give you a sum, which is also an acute angle. Hopefully that made sense. The last one in this section was 13. They gave you a triangle. And they gave you the sides, they gave you this triangle. They told you that this is 6 and this is 9. And this triangle is triangle ABC. And the question was, AC must be smaller than what number? All right, this is what I called it the triangle inequality. Triangle inequality says the sum of any two sides of a triangle, the measures, must be greater than the third side. The sum of two sides of a triangle, measures of the sides, must be greater than the measure of the third side. Therefore, I know that side AC, the sum of these two sides, has to be greater than AC. So 6 plus 9 is 15. Therefore, AC has to be less than 15. The sum of any two sides is, the sum of any two sides, 15, has to be greater than the third side. Then part B said AC has to be bigger than what number? Well, if I add 9, no matter what AC is, 9 plus this side is bigger than 6. So that doesn't help me. But 6 plus this side has to be bigger than 9. The sum of any two sides has to be greater than the third side. So again, 9 is already bigger than 6. So if I take this side and that side, no matter what this measure is, 9 plus this side will always be bigger than 6. But let's go over here. 6 plus this side has to be bigger than 9, which means that AC has to be bigger than 3. Because this number, when added to 6, has to be bigger than 9. So I know that AC has to be bigger than 3, less than 15. You can write this the following way. It's called a string inequality. You could say that 3 is less than AC, which is less than 15. This is a string inequality. In order to write it as a string from left to right, it has to make sense. 3 is less than AC, which is less than 15. Where you cannot use a string if I had something like this. This wouldn't make sense. Hopefully you got this problem. You cannot write a string equality this way. This makes no sense because this says 3 is bigger than x, but x is less than 10, which means that this implies that 3 is both greater than and less than 10. From left to right, it makes no sense. You can only use a string inequality when your inequality symbols are pointing in the same direction. And from left to right, it makes sense all the way across. Is 3 less than 15? Yes. Is 3 bigger than 10? No. But it is less than 10. You can't have one sign going one direction and one going the other. I can't write my string equality this way. This one is a big no-no. All right. Hopefully you've got all the problems on that first page. And then we went to page 27. We started to talk about deductive proofs. And we did a couple of fairly simple proofs. We proved the first one, which I called the right angles are congruent. And I don't think I talked about it, but I told you can write it this way. It's the exact same proof for straight angles. Straight angle, ST. Straight angles are always congruent also because any two straight angles, by definition, a straight angle is an angle that equals 180 degrees. That very simple proof we did for right angles. If you substitute the word straight for right and 180 for 90, it's the same exact proof. Any two straight angles equal 180. Therefore, since they have the same measure, by definition, they are congruent. So right angles are congruent. Straight angles are always congruent. And on page 27, I gave you a couple of problems, a couple of simple proofs. Number number 10. Oh, actually, here you got another algebra problem. Number 10, it said this particular square has a perimeter of 42. Hopefully you remember the definition of a square. It's a four-sided figure where all the sides are the same measure. So this is x plus 3. And they told you that the perimeter of this square is 42, and they asked you to solve for x. Well, perimeter is the four sides added together. X plus 3, that makes this x plus 3, x plus 3, x plus 3. If you add these all together, you get 4x, x plus x plus x plus x is 4x, 3, 6, 9, 12 equals 42. There's your equation. Again, first degree linear equation. You solve by, first bring the 12 over, you have to subtract. Always use the opposite operation. Here you're adding, so to bring it over, you subtract 12 from both sides. 42 minus 12 is 30. You then divide by 4. Now, 30/4 is called a top-heavy fraction. The numerator, the number on top, is bigger than the number on the bottom. And you can always, if possible, you should always reduce a top-heavy fraction to lowest terms. 30/4 has a common factor of 2. If you reduce, you get 15/2. That 15/2 is a perfectly acceptable answer if you want to leave it that way. If you want to turn it into a mixed number, 15 divided by 2 is either 7.5 or 7.5. That's also acceptable. But anytime you have a top-heavy fraction reduced to lowest terms, I will accept it. This is perfectly fine. And the reason I would actually prefer this is because I can't tell you how many times I've seen people get this and then turn it into the wrong mixed number for whatever reason. But if you want, you could write this as 7.5, or you could write 7.5. All three of it would be sufficient. 30/4 is the only one that's not acceptable because it is not reduced. Anytime you have a top-heavy fraction, always reduce it to lowest terms. And then in part B said, if the perimeter were greater than 42, what would we know about the value of x? If the perimeter is bigger than 42, what would be true about the value of x? Well, if it were bigger than 42, that would mean that x would have to be bigger than 7.5. Because if x equals 7.5, the perimeter is exactly 42. If it's less than 7.5, the perimeter would not equal 42. It would be smaller than 42. So if I plug in any value for x larger than 7.5 or 15/2, that would make the perimeter grow and be larger than 42. So that's number 10. Number 15. All right, I told you probably the most difficult algebraic, there were two types of algebraic equations. This is called a simple linear equation. You just have one variable, and the exponent is an understood 1. This is 4 times x to the first power. You don't use a 1 as an exponent. It's understood. If there's no exponent there, it's an understood 1. And then I showed you two other types of equations that we're going to work with. Quadratic equations, an equation where you have an x squared or a y squared or a variable squared, and simultaneous equations. Well, number 15, you get your first quadratic equation. And I showed you one on the board the other day, and I said you factor it into prime factors, and then you substitute. Once you've got your prime factors, you set each factor that contains the variable equal to 0 and solve. Something else, I didn't talk about this, but hopefully when you did this problem out, you thought about it. In problem 15, they gave you the following figures. And again, anytime you have multiple angles at a vertex, they number them. When I talk about angle 1 now, there it is. When I talk about angle 2, there it is. There's no confusion. And then over here was angle D. And I can talk about angle D because there's only one angle in this figure. Something else you'll notice, they put the little arrows at the end. I don't care if you do that or not. This is angle ABC is going to be angle ABC whether you use rays or line segments. It doesn't matter. I told you that by strict definition, the sides of an angle are rays, but you can form an angle using line segments. All right, they told you angle 1 is x plus 7. They told you angle 2 is equal to 2x minus 3. They told you that angle ABC, the whole angle, is x squared. Therefore, x squared is equal to these two angles added together. So here I have a quadratic equation. I have a variable raised to the second power. It's a quadratic equation. Quadratic equations will have possibly two answers. Or you can get one answer twice. It's called a double root. That will happen when you factor, and each of your factors are the same. And then the last part, they told you that this angle is 5x minus 4. We're going to use that at the end. All right, so first I have to solve for x, or I can't determine whether any of these things are equal at all. To solve for x with a quadratic equation, you want to get everything on one side of the equation, the other side equal to 0, and then you're going to factor. So this becomes x squared is equal to x plus 2x is 3x, 7 minus 3 is plus 4. I now want to bring everything to the left side of the equation. X squared minus 3x, bring the 4 over by subtracting it, equals 0. If a quadratic is factorable, it will factor into the product of two binomials. The product of the two first terms has to give me x squared. There's only one way to factor that, x and x. Now, the middle term is a combination of, again, this is that FOIL method. You're going to take a combination of the two outside terms and the two inside terms, and you want to end up with a negative 3x. Well, the only way to get a negative term in the middle and a negative last term is if one of these is positive and one is negative. And in this case, since both of these are the same letter, x and x, I can put plus minus or minus plus. It doesn't matter. It's the same thing. There's two ways to factor 4. 4 and 1, 2 and 2. So there's only two ways to factor this problem. It's either going to be x plus 2, x minus 2, or x plus 4, x minus 1, or, I'm sorry, three ways, x plus 1, x minus 4. Those are the three ways that I can factor this particular quadratic. And very quickly, hopefully, you realize this one doesn't work. X plus 2 times x minus 2, the outside terms and inside terms, negative 2x plus 2x, cancel each other out. You're not going to get a middle term of negative 3. All right, do it this way, and I get x times x is x squared minus x plus 4x is plus 3x minus 4. This doesn't work either. Therefore, here's my only option, and let's make sure it works. X times x is x squared minus 4x plus x is minus 3x. 1 times negative 4 is negative 4. So there's your answer. Plus 1 minus 4. Hopefully you followed that along. And again, if you've forgotten how to factor, please let me know on Friday, and we will do some factoring problems and brush you up on it. All right, once you have a quadratic factored, take each factor that has the variable in it and set it equal to 0 and solve. So either x plus 1 equals 0, meaning x is negative 1, or x minus 4 equals 0, meaning x equals 4. Now please don't stop here, and here's why. These are the solutions to this particular equation. But now remember what we're doing here is we're solving for an angle. And I told you we will never talk about negative angles in geometry, only positive angles. Therefore, you have to take these values for x and plug them in to make sure that when you plug them in, your angle is positive. So if I use a negative 1, I get negative 1 plus 7 is 6. 2 times negative 1 is negative 2 minus 3. Negative 2 minus 3 is negative 5. That doesn't make any sense. You can't have a negative angle. Likewise, if you plug negative 1 in here, you get 5 times negative 1 is negative 5 minus 4 is negative 9. You cannot talk about negative angles in algebra. Therefore, this is a solution to the quadratic equation, but when you plug it into the problem, it makes the problem not work. You cannot talk about a negative angle. So we have to eliminate this root. It won't work in this problem. Try the 4. 4 plus 7 is 11. 8 minus 3 is 5. 11 plus 5 is 16. 4 times 5 is 20. 20 minus 4 is 16. And again, that makes them equal, which is what it said in problem 15. It said, show that angle ABC is equal to angle D, is congruent to angle D. They have the same measure when x is 4. If you plug in a negative 1, you get negative angles. We are not going to talk about negative angles. When you plug in a 4, both angles equal 16. 4 plus 7 is 11. 2 times 4 is 8. 8 minus 3 is 5. 11 plus 5 is 16. 4 times 5 is 20. 20 minus 4 is 16. So here is the solution to your problem, and it makes the two angles congruent. Okay. So much for that section. All right, we then had 1, 6, 8, and 18 on page 32. And we talked about bisecting a line segment. You can bisect a line segment into two congruent segments, and you do that at its midpoint. And a line segment can only have one midpoint. Another way to say that is the midpoint is unique. Unique means one and only one. So if I had a line segment AB, a line segment has a definite length. It's not infinite like a ray or a line. A definite length. AB is a foot long or a yard long or a meter long or whatever. 85 inches long, it doesn't matter, but it has one measure. It's unique. And any unique measure can be cut in half. So if I pick that point and call it C, such that this segment and that segment are the same measure. Tick mark's the same, therefore those two pieces are congruent. That means that C cuts the line segment in half. It bisects the line segment, and you bisect a line segment at its midpoint. And there's one and only one midpoint. Likewise with an angle. Any angle has a unique measure. So here's angle A. Angle A can only have one measure. So if I told you angle A is 50 degrees, it can't be both 50 and 60 or 50 and 30. Angle A is 50 degrees, and one and only one measure can be assigned to any unique angle. Therefore, any angle can be cut into two equal parts, and you have bisected the angle. So angle XAY is cut into two congruent angles by ray AB or line segment AB. You can bisect an angle with a line, a ray, or a line segment. as long as it cuts the angle into two congruent pieces. So the way this is marked, angle XAB and angle YAB are congruent. Therefore, you have bisected the angle. You can cut a line segment into any number of equal parts. You can trisect it, 3 equal parts. You can quadrisect it, 4 equal parts. You can cut it into 5 equal parts, whatever you want. Likewise with an angle. You can bisect an angle. You can trisect an angle. You can cut an angle into any number of equal parts. And let's go over the problems that you had on this page. This was page 32. Alrighty, 32, number 1. It said that again, they kind of jump ahead and assume you recall things. Alrighty, they gave you this circle, and they told you that O is the midpoint of CD. Alrighty, they told you that O is the midpoint of CD, and they said name the congruent segments. Well, if O is the midpoint of CD, that makes this piece congruent to that piece. I hope that nobody said and AO is congruent to OB, because we don't necessarily know that's true. It didn't say O was also the midpoint of AB. The way this is drawn, and again, we haven't really talked about circles yet, but you know what a circle is, and you know the center of a circle is where diameters cross. I'm sure you've heard that word, and where the radii are drawn from. But let me draw this a little differently. If they had drawn it differently, you wouldn't have, I'm sure at least one of you said that AO and OB were congruent. But suppose we had this. Suppose it had been drawn this way. O could still be the midpoint of CD. This can still equal that. But by drawing it this way, it makes it a little more obvious that these two pieces don't have to be congruent. So in problem 1A, the only two segments that you can definitely say are congruent to one another are CO and OD. CO and OD. Everybody understand that one? Again, if you draw it a little bit differently, they didn't tell you anything about this circle other than O was the midpoint of CD. All right, and then in B, they gave you a figure that looks like that. They didn't tell you anything about it. They just labeled it X, Y, W, B, TSR. And they told you that SW they told you that SW bisects XV. SW bisects XV. That means that at W, you're cutting XV into two equal parts. I know nothing else about this figure. I don't know what kind of figure it is other than it has 4 sides. It looks like something that you may have talked about in earlier math classes, I'm not sure. But for our purposes, the only thing you can say is XW is congruent to WV. I know nothing else about that figure that I can deductively state. Okay, hopefully you understand that. Number 6. All right, number 6 said, given that it said that OMP. They told you that OM is x plus 8. And they told you that MP is 2x minus 6. And that OP, the whole thing, is 44. That means from here all the way across is 44. And they said, is M the midpoint of OP? Well, again, this is an algebraic equation. I know that these two pieces, when added together, have to be the whole segment, 44. So I know that x plus 8 plus 2x minus 6 has to equal 44. X plus 2x is 3x. 8 minus 6 is 2. Therefore, 3x subtract 2 equals 42. So x is equal to 14. If x is 14, 14 plus 8 is 22. 2 times 14, 28 minus 6 is 22. If these two pieces are both 22, then you can state, yes, M is the midpoint because OM will equal MP. Again, once you solve for x, plug it in. 14 plus 8 is 22. 2 times 14, 28 minus 6 is 22. 22 equals 22. Therefore, M is the midpoint of that line segment. Okay. All righty, number 8. I hope I'm not doing too fast. Well, you have the luxury of at least backing up and rerunning something, so hopefully that'll work things out. And problem number 8, you're given this figure, and it was what? A, B, C, D, E. And they told you that in the figure, points B and C are trisection points. That means this, this, and that. Those little 3 pieces are congruent. Remember, trisect means cut into 3. Uh-oh. Sorry, my computer blacked out there for a second. All righty, AB, BC, and CD are all congruent. They said that AD, the whole segment, is 12. AD is 12. Well, if AD is 12 and all 3 of these sections are the same, that means each of them has to be 4. So this is 4, 4, and 4. Because they're congruent. And 3 times 4 is 12. So AB is 4. AC, from A to C, is 4 plus 4, or 8. Okay? And then they said, well, suppose that AB is x plus 3. Solve for 8. Well, x plus 3 has to equal 4. Solve for x, excuse me. So you get x would have to be 1. If AB is equal to x plus 3, then x would have to equal 1. If AB is equal to x plus 3 and AE is equal to 3x plus 6, find AE. Well, we just solved for x. X would be 1, and they said that AE is 3x plus 6. So you simply take that 1 and plug it back in. 3 times 1 is 3, plus 6 is 9. And then part E. What segment is C the midpoint of? What segment is C the midpoint of? C is the midpoint. Well, since BC and CD are equal, then C is the midpoint of segment BD. It cuts the segment BD in half. Do rays EB, do these two rays trisect the angle? Well, these points cut the side in 3 equal parts, and I am going to venture a guess that a lot of you said, yeah, since these are equal, then these angles have to be equal. And unfortunately, that is an incorrect assumption. You cannot say that. Just because these pieces are equal, that doesn't translate at all to the angle across from them. I know nothing about these 3 angles. I cannot make any deduction whatsoever about the measure of those 3 angles. So the answer is our B and C, our rays EB and EC, rays that trisect the big angle AED, and the answer is I have no idea. No, just say no. You don't know. Okay? And we'll talk more about that as the course goes on. We'll be able to prove that they're not, in fact, going to be equal. Right now, you just say, I do not have enough information. I do not know. And then the last problem you had on this section was problem number 18. And in problem number 18, you were given this figure, and you were told that 3x, 4x, 3x, and 2x. And again, remember, a drawing is only a visual aid. It does not have to be to scale. And in 18, they told you that this was F, J, G, and H. They told you that rays OG and OH cut the straight angle. They told you that, they gave you that was a straight angle, angle FOJ. This is a straight line. And they cut it into 3 parts with a ratio of 4 to 3x, 4x, 3x, and 2x. And they asked you, or they said that it was cut into parts in a ratio of 4 to 3 to 2. So if I call this one 4x, this is 3x, that's 2x. 4x to 3x to 2x is the same as 4 to 3 to 2. And they asked you for the, find the measure of angle FOG. Find the measure of FOG. So in order to find FOG, I have to first solve for x, and then substitute x right there for the x. And what I'm going to use is the fact that a straight angle is 180 degrees. That means if I put these 3 pieces together, it equals 180. Again, just a first degree linear equation. 4 and 3 is 7, plus 2 is 9x equals 180. So x is equal to 20. Therefore, angle FOG is 4 times 20, which is equal to 80 degrees. So 4x, angle FOG, is equal to 4 times x, which is 4 times 20. Your final answer, 80 degrees, if you want to put degrees in. And that is it for your homework. Hopefully you got it all. And again, we don't have the luxury of I don't have the luxury of answering any questions that you might want to ask. but you can run this thing back and forth. And also, again, if that doesn't help, please call me or email me, and I'll get back to you as soon as I can. Okay? Alrighty, new info. I talked a little bit about this. Let me talk more. The deductive structure. There are two types of logic, deductive and inductive. Inductive, you go from really, really general statements and make a very specific, or you go from very specific statements and make a very general conclusion. An example of inductive is, it rained yesterday, it rained today, therefore I can conclude it's going to rain every day for the rest of eternity. You've taken two specific days, two very specific days, and made a very, very general conclusion. It rained yesterday, it rained today, therefore I can conclude it's going to rain every day for the rest of my life. That's not valid reasoning. You can use inductive logic in certain sciences because it's impossible to do an infinite number of experiments. You can only do a finite number of experiments in biology, and with that finite number of experiments, you can make a fairly valid conclusion. But mathematically, we don't like it. We like deductive reasoning. Deductive reasoning goes from very, very general statements, and you can make a very specific conclusion. An example of deductive reasoning. Chicago is in the state of Illinois. Joe lives in Chicago. Therefore, I can deductively conclude, taking those two general statements, I can make a very specific statement about Joe. Joe lives in Illinois. Chicago is in the state of Illinois. Joe lives in Chicago. Therefore, Joe lives in Illinois. I've taken general statements and made a very specific statement. That is deductive reasoning. That's the deductive structure. Now, I told you that in this class, we're going to use definitions. A definition tells you what something is. You can't prove or disprove a definition. It's telling you this is it. An angle is a right angle if it measures exactly 90 degrees. That's the definition of a right angle. I can't prove that. I can't disprove it. They're telling you what the right angle is. One thing about a definition, we have what are called a conditional statement or an implication, if then. If an angle equals 90 degrees, then the angle is a right angle. This if part, sometimes referred to as a hypothesis. The then part is called the conclusion. If A, then B. A definition will always be reversible. That means if I flip the if and then parts, it'll still be true. A definition must be reversible. So if I wrote this in the other direction, it will say, if an angle is a right angle, then the angle equals 90 degrees. This is also true. If you have a definition, it doesn't matter which way you write it. You can interchange the if and the then part, and they're always true. We'll talk more about this later, but a good definition has to be reversible. And again, anytime you have an if-then statement, it's called an implication or a conditional statement. The first part is called the hypothesis. You can also hear that the then part is referred to as the conclusion. These two are called converses of one another. When you interchange the if and the then part, you have what is called the converse. And every definition has to be reversible. sometimes referred as an implication. If A, then B. That's a conditional statement. Converse. The converse of any implication or any conditional statement, you interchange the if and the then part. So the converse would be if B, then A. So a definition can always be written as an implication or conditional statement. And every definition has to be reversible. In other words, every definition and its converse will always be true. That is not the case with all statements, and we'll talk more about that. But something else that we're going to talk about in the deductive structure are we're going to talk about implications. We're going to talk about definitions, implication, and definitions. We're going to talk about conditional statements. We're going to talk about theorems. A theorem, T-H-E-O-R-E-M. A theorem is a statement that we will prove. And once it's proved, we never have to prove it again. It will be true forever. But before we accept it, we will have to prove it. There are also postulates. A postulate is a statement that will be accepted without proof. It's not like a definition. It doesn't tell me anything. It doesn't say this is the case. But there are certain problems that we will get into in geometry where we need to know something is true, and we're going to just accept it as being true. That is called a postulate. And then statements that are very much related to theorems are called corollaries. In other words, it's kind of an addition to a theorem. So those are statements that basically we will prove also. So theorems and postulates may or may not be reversible. A definition must be reversible. A theorem, not necessarily. Let me show you that. We proved one theorem. We proved it the other day. Well, actually two. We said this: if angles are right angles, then they are congruent. That was the first theorem we proved it. If any two right angles are congruent. If angles are right angles, then they are congruent. If I turn that around, it becomes if angles are congruent, then they are right angles. That's not necessarily true because I could have two angles that are both 30 degrees. They're congruent, but they are not congruent. But they're not right angles. This is always true. If angles are right angles, then they are congruent. But when I turn that around, I get a statement that isn't necessarily true. If angles are congruent, then they are right angles. The only angles that are congruent are not right angles. You could have 30-degree angles congruent, 37-degree angles are congruent to one another, two 40-degree angles are congruent, but they're not right angles. So this was a theorem. We proved this statement. Theorems are not necessarily reversible. Some will be, but some will not be. Here's a case where the first one we talked about is not reversible. A definition will always be reversible. The definition of a right angle. An angle that is a right angle is an angle whose measure is 90. Turn that around. If an angle has a measure of 90, then it is a right angle. A definition is always reversible. That means it'll be true in both directions. A theorem, not necessarily. Hopefully that makes sense. And you're going to also see this symbol. So, that's a shorthand method of writing if A, then B. So that little double arrow, looks like an equal sign with an arrow on it, means if then. So that's another way of writing it. So this is equivalent to that. It's just a different way of writing it. Now, we're going to do a very, very little bit of logic, symbolic logic, and it can be confusing, but I want you to know a few things. All right, here's my implication. If P, then Q. Again, this little arrow, this little equal sign with an arrow means if P, then Q. The then part is always at the end of the arrow, where the arrow is pointing. So if P, then Q. That's your implication. And we've talked about the converse. The converse, you interchange the if and the then part. So the converse of this statement is if Q, then P. This is called symbolic logic. I'm using symbols here. Something else that we're going to learn is this. This little squiggle in front of a letter means not P. So if I define P as P is it is raining, then not P means it is not raining. So the negation of a statement is just the opposite of what the statement says. It is raining. That's how I define statement P. So not P, it is not raining. Likewise, if I started with this, if P is now it is raining, then not P is it is not cancels each other out, just like two negative signs. So the opposite of not raining is it is raining. Okay? So again, either way. And again, any not P is equivalent to P. When you have two negation signs, just as in algebra, a negative, when you negate a negative, they cancel each other out. So not P is exactly the same as saying P. Now, why did I give you this? Because there's two other types of statements we're going to talk about. The original implication, the converse, the inverse. The inverse of a statement is found by negating both halves of your original implication. So if my original implication is if P, then Q, the inverse is if not P, then not Q. You take the original implication and negate both sides. And the third thing we're going to talk about is the contrapositive. The contrapositive is the combination of these two. You're going to take the original statement, take the converse, and negate both sides. So the contrapositive, turn the original statement around and negate both halves. Implication, if then. Converse, interchange the if and then. Inverse, negate both halves of your original statement. Contrapositive, turn it around, turn the original implication around and negate both halves. So the contrapositive is actually the converse and inverse combined of the original statement. Turn it around and negate both halves. Now again, depending upon the statement that you work with, well, let me just give this to you. what these mean is the following. If my original statement is true, the contrapositive will also always be true. These two statements, an implication and the contrapositive, always have the same truth value. If one is true, the other's true. If one is false, the other's false. The same is true about these. If an inverse of a statement is true, then the inverse of the statement is also true. If this statement were false, when you turn it around and negate it, that is also false. The inverse will be false. So if this statement is true, that statement is true. If this statement is false, that statement is false, and vice versa. If this is true, the contrapositive is always true. If this statement is true, the contrapositive is, or excuse me, if this statement is false, the contrapositive is always false. Inverse and converse always have the same truth value. If one is true, the other is true. If one is false, the other is false. A statement, an implication, and the contrapositive will always have the same truth value. If one is true, the other is true. If one is false, the other is false. Now, we're not going to do a lot with this, but I am going to give you a couple of problems for homework. And what they want you to do in these kind of problems is they want you to turn a given statement into symbols, and then they're going to ask you to do things with it. Let me show you one. Alrighty, this is you know what? This is a little bit confusing to do on this board. I'd rather have you in front of me. I'm going to talk about the remainder of this stuff, and I won't even give you a homework problem. We'll do a couple problems in class because it's much better in person where I can answer questions, because there are going to be questions with this. But this is called symbolic logic. All right, now the last thing I want to talk about for today is probability. And these kind of problems are going to pop up throughout the course, but we're not going to do a whole lot with probability throughout the year. We'll get a few questions here and there, but the probability of an event is the number of successes over the total number of outcomes in an experiment. Example. Hopefully everybody knows what a single die is. Plural dice. When you have a pair of dice, if you just have one of them, a die is a cube, and opposing faces of the cube have numbers on them that always total 7. So there's a 1, and on the bottom would be a 6. If you have a 2, the opposing face would be a 5, and if you had a 3, the opposing face would be a 4. So when you roll a single die, only 6 things can occur. You get a 1, 2, 3, 4, 5, or 6. That's all that can happen. So if I said we're going to define an event, E is roll a die. Again, a die is the singular version of a pair of dice. If I said, what is the probability of rolling an even number? So if I roll a single die, what's the probability that an even number will show up? Well, when I roll a single die, let's do the bottom part first. The total number of outcomes. When you roll a die, there are only 6 things that can occur. And again, when you roll a die, you're concerned with the number that's on top. The one that's on top showing, that is when you roll a die, that's what's considered the number that comes up, the one that's up. There's only 6 things that can happen. It could be a 1, 2, 3, 4, 5, or 6. That's if you're using a regular cube. Now, there are games out there that have die with multiple numbers of sides. I'm talking about a pair of regular dice, 6-sided dice, cubes. And the total number of outcomes when you roll a single die is 6. You can get 6 numbers. 1, 2, 3, 4, 5, or 6. Now, I said, what is the probability? The little p out front means probability of an even number. So the number of successes, there are 3. I could roll a 2, a 4, or a 6. That's it. So the total number of successes would be 3 over the total number of outcomes, which is 6. Therefore, the probability is 1/2 or 0.5. The probability of any event, no matter what event you talk about, has to be 1 or less. You can never have a probability that's negative. You can never have a probability of greater than 1. The probability of, it's got to be between 0 and 1. The probability of 0 means that it's an impossible event. Like if I said, if I roll a single die, what's the probability of rolling a 7 with that one die? Well, there is no 7 on a die, so the probability would be 0. If I said to get a probability of 1, if I roll a single die, what's the probability of getting a number between 1 and 6? Well, that's the only thing that can happen. It happens no matter what you roll. Therefore, the probability of rolling a number between 1 and 6 is 1. A probability has to be between 0 and 1. 0 means it's impossible. 1 means it's an absolute certainty that it will occur. The probability of any event has to be greater than or equal to 0, less than or equal to 1. The kind of problems that you're going to see are things like this. All right, I give you those 4 angles, A, B, C, and D. A, again, the drawing is only a visual aid. They don't have to be anywhere near close. 40, 60, 24, and 80 degrees are those 4 angles, A, B, and D. If I said, if I pick, let event E be, pick 2 angles. Pick any 2 angles. What is the probability of getting a sum excuse me. Event E is going to be, I'm going to pick any 2 of these 4 angles. What is the probability that when I pick those 2 and add them together, their sum is less than 90? Added together, their sum is less than 90. Well, first of all, we have to figure out the number, what's the total number of outcomes? Now, I could pick A and B, that's 1. I could pick A and C, that's 2. I could pick A and D, that's 3. I could pick B and C. I don't say B and A, I've already picked it. A, B is the same as B and A. So I've got B and C, that's 4. I could pick B and D, that's 5. And I could pick C and D, that's 6. There are 6 possible outcomes. Again, there are 6 outcomes. I can go AB, AC, AD, and it doesn't matter which I pick first. When I pick A and B, it's the same as picking B and A. You don't do it twice. I can pick B and C, B and D, and then C and D. Those are the only 6 outcomes. I hope you understand that. Again, AB is the same as BA. AC, same as CA. Doesn't matter which order. A and D. Then go down to B. Well, I've already got B and A, so I go BC, BD. Then I go down to C. Well, I've already got CA, I've already got C and B. Therefore, C and D is the only other option. There are 6 possible outcomes. Of the 6, when you add the 2 together, you get less than 90. Well, 40 plus 60 doesn't work. 40 plus 24 works. 40 plus 80 doesn't work. 60 plus 24 is less than 80. 60 plus 80 doesn't work. And 24 plus 80 doesn't work. So there only seem to be 2 solutions. AC works, BC works. So of those 6 possible outcomes, 2 of them will give you a sum less than 90. Therefore, the probability of this occurring is 1/3. You can write a probability as a fraction reduced to lowest terms, 1/3. You can write it as a decimal. It doesn't matter. But again, I mentioned the probability of any event occurring has to be greater than 0, less than 1, or equal to 1. So if you end up with a negative number, or if you end up with a number bigger than 1, you have made a mistake. So go back and check your work. These are the kind of probability problems that we're going to see, and we're going to get them periodically throughout the whole course. And again, I will talk to you more in class about the symbolic logic. It's going to be a little bit easier to explain to you face-to-face because I know you're going to have questions. And I can't answer them right here, and I don't want to just write it all up. It's a little bit confusing. That's all I want to talk about. So for Friday, please do the following problems. Page 42, numbers 5, 10, 11. Page 51, 1 through 5. Page 42, 5, 10, 11. Page 51, 1 through 5. Again, if you have questions, my cell 240-701-4470 and RollyDean2000 @gmail.com. It's not going to fit. I apologize. Okay? And again, I look forward to meeting you I've already met you. I look forward to seeing you again on Friday. Make sure you smile. Have a wonderful week. I'll see you on Friday. Bye-bye, everybody.